Here's an FRQ that comes from a non-calculator section, so put your calculators down. Don't use it on this one. I chose this one because it goes through tangent lines and area and things that we're used to working with, but it puts a little twist on it in that it does it in a very generic fashion. So we have a lot of problems where they'll do that. Well, they'll use like the letter K, or in this case they're going to use the letter A, and ask you to do what you're used to doing, but when it becomes generic, it a lot of times becomes a little more difficult. So for this problem, you're presented with a picture, and underneath the picture they give you a little bit of information. They tell you the function that you're working with is the function 4 minus x squared, so a parabola, and they have the region R, which is a very small region. You'll look here, R is just this piece right here, and that is in the first quadrant, and it is bounded by the graph of the f function, the 4 minus x squared, and then the tangent line that is tangent at x equals a, and goes through the and bounded by the y-axis. So first part, question A, is asking you to write an equation of the tangent line in terms of A. So what that means is we need to do what we normally do with slope and x and y, but our answers should all be in terms of A. You're going to still have it be generic. So for part A, the first thing that you need when you write a tangent line is you need a slope. So my derivative of my function, if my function is 4 minus x squared, then the derivative of that function is negative 2x. And then they tell us the point we're working with is right here. The point is the point A, and then 4 minus a squared. So my slope, when I put a in, is negative 2a. So that is my slope. My coordinate is right here. It's the x and the y that is listed. So when I do my equation, I can either do y equals mx plus b, or I can do point slope. It really doesn't matter. I actually started it as as a point slope, but you could do it as y equals mx plus b. Either way would be fine. If you go y equals mx plus b, you would have y is 4 minus a squared equals your slope is negative 2a, your x is a, and then plus b. We get 4 minus a squared equals negative 2a squared plus b. Add this to the other side to get b. So we get our b value to be 4 plus a squared. So my tangent line is the equation y equals m, which is negative 2a, x, which is just x, plus b, which you can write as a squared plus 4 or 4 plus a squared, and this would give you full credit for part A. My guess is part A would be worth at least 2 points, probably 2, because they're checking to see if you can correctly find the slope, which is just deriving it and putting the a value in, and then you can take that with the point that you know and write your equation for your tangent line. One thing to be careful with is you really, because of the way they say it, because they say they want the equation line in terms of a, you really want to get in the habit of writing y equals and then having everything else that has an a value on the opposite side. So you really have an equation written as y, which equals something in terms of a. So that's the first part. Second part wants to know an integral expression that gives the area of region R. They don't actually want to find the area, they just want the integral that would set it up. So for my region R, it goes from 0 to a, and I know some students might be tempted to say, well, it kind of looks like it goes to 1, but we don't know that for sure, so we can only go with what we know, which is it goes from 0 to a. And then it is top minus bottom. The top is the tangent line, which I'm going to use what I just had in part A. My tangent line was negative 2ax plus a squared plus 4. So that's my top. And then minus the bottom, which is my parabola 4 minus x squared. If you want, you can distribute the minus sign and cancel. You actually could have your 4's cancel, or you could leave it just like this and get full credit. My thought on this one is this part is probably only worth 1 point because you're just setting it up. You're not asked to actually go through and do an integration. That's what you're going to be doing in the next part. Letter C wants you to now get an expression for the area without an integral sign. So what this is saying, when I first read it, it kind of sounds a little strange, is I actually want to integrate it. So I'm not going to leave the integral sign in there. I'm going to get an answer after the integration has been done. So if you go to what I just wrote on part B, so I have this integral. And one challenging part about this problem is the parts are very dependent. like part B and part C are so closely related, and then you'll see that part D is very closely related, and then part A helped you get to part B. So that is the tough part about these problems, is you really have to start them off strong so you can continue through. One thing that might make it easier for you is you can cancel the 4s because you're on a 4 and a -4, so that's just going to make it a little simpler. And then I'm going to go through and integrate it. I'm going to integrate everything in terms of x. So I'm going to have negative 2a x squared over 2. I can cancel the 2's right away if I'd like. Plus a squared x. Remember, a is just a constant. So when I integrate a squared, I just get a squared x. And then this is going to be a minus, so I end up with plus x to the third over 3. And I'm going from 0 to a. Put my boundaries in. I get negative a times a squared plus a squared times a plus a to the third over 3. When I put 0 in, I will get 0. So I don't have to worry about that. The first two terms will cancel. I end up with a negative a cubed and a positive a cubed, so that will cancel. So my final answer for this part is a to the third over 3. This part, again, at least 2 points, probably just 2 points. Possibly you get a third point out of this. You're making sure you integrate correctly and you plug your boundaries in. But as long as you have everything correct in part A and part B, part C is actually pretty easy. Part D I thought was the toughest part when I went through this question, because when I first looked at it, I immediately started doing something wrong, which I think a lot of students is going to have the same tendency that I started with. First thing I thought when I thought average value, I said, well, average value is just the area divided by the width. And I just found the area in part C, so I'm just going to take that answer and divide by the width. Here's the problem with that logic. That is the average value of the function. If I want the average value of the area, I actually have to integrate the area that I just got from 0 to a. And then I need to divide by 1 over, or multiply by 1 over a, or divide by a. So the area that I just got in part 3 was a cubed over 3. Now they did want it to have it in terms of x's because we have to integrate in terms of x's. So I'm actually going to integrate the function x to the third over 3. Saying that my a will actually represent some x value. So I'm going to integrate in terms of x's. So I'll put my little dx there to remind me. So I get x to the fourth over 4, but there's already 3 there, so it's going to be x to the fourth over 12. I'm going to put my boundaries in. So I get a to the fourth over 12 minus 0. That is like the area of the area is the best way to explain it. That's what I get with area. I want the average value of the area, so I'm going to multiply that by 1 over a, or divide by a. This a will cancel with one of these a's, giving me a final answer of a to the third over 12. I think D is the toughest part. It seems like it's easy. When I first started this problem, I just took what I did in C and divided it by A. But what you have to keep in mind is that's the average value of the function. When you want the average value of the area, you actually have to integrate the area. So anytime it's asking for the average value of something, you are going to integrate that particular component, that particular amount, that equation, and then divide by the width of the interval that we're working with. So that is how you get D. To me, D is probably worth the 3 points. It might be the one part. Even though there's not a ton of work, it requires you to understand not only how average value works, but making sure you're taking the average value of the right piece, and then doing the integration correctly and plugging the boundaries in. So this question I thought was interesting. I think that the first 3 points are pretty attainable because we are so used to tangent line and area, but it definitely has some challenging parts at the end that make it a really good practice problem for looking at generic ways to represent area in tangent lines.